Hey, what's up, YouTube? Welcome to another math stream today. I am just here practicing math every day because I've got too much free time. So this week we are working on calculus, which is fun. And we are working through this beautiful book by Taalman and Kohn. I'm tutoring a student in calculus right now, and she brought this book, and I was just like, whoa, this is beautiful. This is really nice. I've never seen like a freshman 3-semester course in calculus out of such a nice, elegant book. So highly recommend this one if y'all want an alternative to Stewart. It doesn't have cartoons in the margins and things like that. There are no cartoons in this book. So yesterday we defined the intuitive definition of a limit, which is a familiar notion. Everybody who learns calculus learns the concept of a limit. In some real sense, it's the most important idea in calculus, I think. And something that struck me about this book, when I saw it, I was like, oh, this is a legit book. It includes one scary definition of the limit. It doesn't just include the straightforward one, but it also includes a slightly scary version. And as a former math major myself, I know how scary this road goes. So today, I wanted to review the intuitive definition that we got yesterday and the formal definition according to Taalman, which is a pretty nice definition. But then we're also going to get some exposure and take a look at what Spivak calls a limit, what Rosenlicht calls a limit, and then what Gamelin Greene calls a limit. I haven't done math, especially pure math, in a very long time, and this stuff is terrifying me. So let's get into it. This is going to be fun. Let's get the iPad up on screen. I don't think we're going to do any problems at all today, so if you're just here for help on your homework, check out another video. We'll get back to the problems starting tomorrow. I've already spent too much time just writing these things out, so let's get into it. Okay, my iPad is not working correctly yet, but now it is. All right. So, this was fun to put together. I'm calling this a scary definitions of a limit presentation. My handle is the math hobbyist. And throughout, I thought it was fun to just try to write down a little bit of historical context about all of these ideas. Something I want to convey in this video is that math is not done. Math has not been solved. A lot of math is still being created and invented, and some things that you take for granted is actually relatively super new. Like Hardy, I just learned for the first time today, Hardy in 1908, just barely 100 years ago, a little more than 100 years ago, he's the one who started writing a limit in this way. Like limit with x arrow c under the limit. I thought that was really neat to learn. So reviewing the intuitive description and notation for limits. First off, the idea of a limiting process, that goes way back in history, back to Euclid. Euclid's Elements is considered one of the, if not, it is considered the single most successful mathematics textbook of all time. And Euclid considered sequences like 1/2 plus 1/4 plus 1/8 plus 1/16 plus ... And what happens when you keep adding more and more terms in this sequence. So Euclid studied sequences and limits of a sequence, and then I don't know when, but somebody at some point, potentially it was Newton, started studying limits of continuous functions. All right, so an intuitive description and notation for limits. Suppose f is a function and L and C are real numbers. Definition of a limit. If the values of a function f of x approach L as x approaches C, then we say that L is the limit of f of x as x approaches C, and we write this notation. Okay? And then she also defines limit at infinity, infinite limit at infinity, these other types. But broadly, hey, good day to you, Sam. Thanks for tuning in. This is going to be a fun little lecture thing. Not lecture, but practice stream. It is a practice stream. All right, I wanted to get a copy before I start writing everywhere in this. So here, the important thing is we have the idea approach, like approaching a value and approaching a number. So that's just saying if you have a curve of some kind or a function, like as x approaches and gets close to this point, then the y values approach this. The y values approach this single number L. Okay? So nearby, like near the point C, the value is getting really, really close. It's approaching the value L in this case. All right. But then what I like so much is that she calls it out. She just calls it, this is an intuitive concept. And then in the next section, she actually writes out the formal definition of a limit. And just for a moment, I wanted to say that I learned this today. It wasn't until Weierstrass in 1861 that we put the limit, the idea, that squishy, informal definition of a limit. It was only in 1861, like not even 200 years ago, that we came up with this concrete idea of what a limit is. How's it going, Sam? How's your day going? Good to see you. All right, so the limit with this notation that was actually invented later, but this notation means that for all epsilon greater than 0, for all numbers, there exists another number such that if x is in one of these two intervals, so it's really close to C, but it's not exactly C. Notice that we have a union, and we do not have the number C in this interval, in this union of intervals. But for any number close to C, then f of x is in L minus epsilon and L plus epsilon. So what's the current topic? The current topic is calculus and the definition of a limit. So in that drawing that I had, this here is this is that neighborhood around the point C. So this is C minus delta to C, union C to C plus delta. So we have like a little neighborhood, like all the numbers to the left and to the right. And then we have some kind of function, whatever. And then maybe those should be green, but whatever. Yeah, they should be green probably. And then what we say is that no matter, let's see. No matter what, yeah, for every x value within the interval that I drew in the x-axis, without that one spot, C, in that x-axis interval, every y value is within this, is within L plus epsilon to L minus epsilon. Okay, so here we get everything within that neighborhood is within that little, within the desired accuracy of the function. So just stare at that for a while, let it soak in. It is a beautiful statement because it puts this squishy idea of approaching L and approaching C, it puts it on some kind of firm ground. It actually says it's a game, okay? Like we have a game, and the game is you pick any positive number. You pick any positive number. It could be 10, it could be 0.00001, it could be whatever you want, like 100 nines or 100 zeros in a row and then a 1. But you pick any number, and I'll find a small neighborhood such that I'll find a small neighborhood around the point C such that the value of the function is close, like it's within the desired accuracy of the limit number L. So that's, again, we are now in the land of metaphors. This is not rigorously stated here. The rigorous definition is here, but it's good to go back and forth between rigor and metaphors. Rigor and metaphors. So formal definition. This is definitely closer as an intuitive definition than this. Okay, so okay, Sam asked, what is standard nomenclature for the last number? Is it C minus delta or C plus delta? I'm looking to clear that up in my mind. Okay, so this is the neighborhood. This is the neighborhood around the point, because we are defining the limit at C. We're defining the limit of a continuous function at a point C. Or I shouldn't say continuous function. We're defining the limit of a function at a point. And that is, it says that delta is some small neighborhood around the point C. So, for all x such that C minus delta is less than x. Well, x, it's kind of hard to write this and not make it look just like ever so slightly scary. C minus delta to C union C to C plus delta. So you could also, I think that it might look clear if we say x is in C minus delta to C plus delta, and x is not equal to C. This may be a little bit clearer to see. To see, unfortunately. That's a little pun. So in that small neighborhood where, so here I have it drawn in the x-axis in green, except for that one point. Like any x value in that neighborhood will be within the desired accuracy. Like within this I shouldn't draw all those little lines. I'm going to say all of these y values right here of the function are close to the number L. The number L, we say, is the limit. Here was just one example, but then if the thing is that delta depends on epsilon. Okay? If epsilon is 0.1, epsilon equals, let's say if epsilon is 1, and we are doing a elevator back of napkin calculation and the function doesn't need to be very accurate, then maybe, for example, delta can be 10 or something. But then maybe if epsilon is 0.001, if we need it to be that accurate, if we want that amount of accuracy, then delta might need to be 0.1 or something. But the point is that for all epsilon greater than 0, there exists a delta. And delta always depends on what epsilon you choose. That's why I call it a game. If you pick a small number, I'll find another number. I'll find a neighborhood such that this is true. Yesterday, I came up on the fly with the concept of gerrymandering, which I don't know how well that metaphor works. I haven't thought it through well enough, but I think it kind of works. It's like if gerrymandering, for those who don't know, is the process of redrawing political maps. And if you want to prove that the result of an election is L, a result of an election, then I don't know, I don't know what epsilon would be exactly, but delta is the neighborhoods. It's the political map that you draw. You redraw the political map so that everybody within those neighborhoods vote the same way. Vote close to L. Okay? So, like, in this metaphor, X in the neighborhood are the voters. For every voter, yeah, the voters, enough voters vote so that the result of this election is L, if that makes sense. It's kind of a weird concept, but I think as a metaphor it kind of works. Gerrymandering. And there's a reason I came to that thought. It's that literally these are called neighborhoods in higher math. And we will see that soon. Okay, any questions? So this is a formal definition, and I just thought it was so cool that Taalman actually shows the formal definition. And then there's another section in Taalman's book where quite literally there are a lot of proofs that you do. Again, I said that delta depends on epsilon, so you want to prove that some function is continuous at this point or has a limit at one point. And so in some sense, it's like the problem says, for this epsilon, find a corresponding delta. For this epsilon, find a delta, such that all of the constituents vote the same way or close enough to one another. Or the harder problems are like prove that this statement is true, prove that this function is continuous, and then it says no matter what epsilon you pick any positive number, find a delta that works depending on what epsilon you chose. Anyway, so that's a cool mathematical statement, I think. I just think it's beautiful mathematics. But this goes a little bit further. So limit of a sequence. This is Cauchy in about 1823. Cauchy defined this idea, and he defined convergence of a sequence of numbers. So a sequence can be a sequence like 1/2, 1/4, 1/8, 1/16, ... Right? These are the powers of 2, division by powers of 2. We know that the sequence 1 over n, as n gets big, this is going to get really close to 0. And so what we're finding here is instead of a neighborhood and a continuous or smooth function that's defined on all of the real numbers, this is a sequence, and it's just a list of numbers, but it's going to be the same idea. We are still going to pick for any epsilon greater than 0, arbitrary positive number, 0. Whatever, there exists a delta greater than 0. Oh wait, in this case it's not a delta. In this case there's a number n such... So this is a number. Like 1, 2, 3, 4, 5. Such that the nth term is less than L when n is greater than capital N. So if I say, we know that the sequence, just intuitively, we know that the sequence, sorry for my feet, we know that the sequence is going to tend to 0. So 1 over n tends to 0. What if we pick epsilon to be 0.5? Well, I think n equals 1 works. Because for every Sn after it, every number after 1/2 is always less than 1/2. All of these numbers forever are less than 1/2. Right? So that's for this specific epsilon, but then if we chose epsilon being 0.005, we'd have to take a lot more terms in the sequence until all of the numbers are less than 0.005. But at some point, this sequence, every number is going to be less than whatever number epsilon you choose. Like, let's get another concrete example. If epsilon was 0.1, 1/8 is 0.125, and 1/16 would be 0.0625, right? So then when epsilon is 0.1, then every number after n equals 3 is going to be less than 0.1. 0.125, like every number after 1/8 is less than 0.1. So that's cool. So now we are talking about a limit, but we're no longer talking about functions of real numbers. Hey, I think we need Sn minus L less than epsilon for n greater than or equal to n. Yes, absolutely. Yes. Yeah, you're absolutely right. I miswrote that. Thank you. So we do need that intuitively Sn is close to L, which means, in other words, is less than epsilon. I miswrote that. Okay, yeah, that is the right way to write that down. So the distance between Sn and L is really small. Yeah, okay, so I got that just a little bit off, but here's the formal definition written down in Ross. So this was my first undergraduate analysis class. Analysis is theoretical calculus, and again, Cauchy is the person who really wrote down and formalized the idea of limits of sequences. Yeah, why are we doing this? It's because some engineers tried to claim that all functions can be written as combinations of sine and cosine, and mathematicians were really angry about that and said, this doesn't make any sense. And Fourier was like, but it works. And mathematicians were like, I don't understand why it works. We have to figure this out. And that's not completely true, but it's sort of, kind of true. All right. So in about the 1800s, we started making a lot of mistakes in mathematics. Mistakes were popping up, and things were just didn't make complete sense. Things weren't on formal, firm ground. And mathematicians did a lot of work to try to formalize this idea of a limit. All right, so let's just read it out. Ross. This is a great book in undergrad analysis. A sequence Sn of real numbers is said to converge to the real number S, provided that, and then here's the important meat that Ben just referred to. For each epsilon greater than 0, there exists a number n such that n little n greater than big N implies that the distance between that term and the limit point is less than epsilon. So at some point, all of the numbers in the sequence are close. This is like Sn is close to S in his notation. If the sequence Sn converges to S, we will write the limit n approaches infinity, Sn equals S, or Sn arrow, Sn tends to S. The number S is called the limit of the sequence Sn. A sequence that does not converge to some real number is said to diverge. So now we're getting to the same ideas, but now we're just talking about sequences. I will note that Taalman, in this section, I think, on the formal definition of a limit, Taalman does put a thinking forward exercise. Thinking forward is like, think about this new idea. We're probably going to come back to this in the future. And Taalman does define in that exercise the limit of a sequence, and she hints to calculus 2 calculating series. So like what Euler, or not Euler, Euclid, I wrote it down somewhere. Euclid was considering, what if you take half of a step toward a door, and then you take another half of a step, and then, like, what if you take half the distance toward that door, and then half of the remaining distance, and then step forward another half of the next distance? If you add all of these numbers, 1 over 2 to the n, it'll take you an infinite number of steps, but you'll always be less than the full distance, but this is going to approach 1. So, I don't know, I thought that was cool. Yeah. So this is a series, and you can think of a series as a sequence. So if you take just one step, that's 1/2. If you take 2 steps, then that would be 3/4. We add the first 2 terms, and then we add 1/8, which is going to be 7/8. And then ... This sequence, at some point, no matter what epsilon you choose, a term will be close to 1. By close, I mean that the difference of the term and 1 will be less than whatever epsilon you choose. Okay, so that is, again, Euclid considered this idea of a sequence or a limit of a sequence in 300 BC. Yeah, so that's Ross. And then we jump forward many chapters. This is chapter 7, section 1. We jump forward many sections, and now we're in chapter 17, section 1, continuity of a function. This is on page 124. Let f be a real-valued function whose domain is a subset of R. Okay, the function f is continuous at a point x0 in the domain of f if, for every sequence in the domain of x converging to x0, we have the limit of the function equals f of x0. If f is continuous at each point of a set, then f is said to be continuous on that set. The function f is said to be continuous if it is continuous on the entire domain of that function f. Okay, so this is the same idea but different terms, just it's defined and presented a little bit differently. But notice that in this definition of a function, the continuity of a function, we're talking about sequences of points in the domain of f. So for every sequence that converges to a single point, then we have let's see. If we have then this is for every sequence of in the domain, we have the sequence f of x1 if this sequence of the function values converges. This is this, how does he write it? He writes it like this. I think that the sequence of the function values converges to. So now we have a function and we are defining the continuity of a function based on the sequences of input values and the sequences of output values of that function. So that's kind of cool. Like, big picture, engineers like Newton and others just talk about a function and it just gets close, like the values get close to a point, and then we make a big jump to get to this, and I'll skip that for a second. Mathematicians talk about just a simple sequence of numbers, like a list of numbers, and then you define the function approaching a value if every sequence of input values has the output values also converging. So we define the function, the limit of a function based on sequences. So in one textbook you define just kind of like surface level. In another textbook you say, well, that surface level also depends on something deeper. Like, this concept of a limit depends on the concept of a sequence. So we're going to study sequences for a little while. These are called Cauchy sequences, named after the guy Cauchy who came up with these ideas in 1823. Okay, let's keep going. And now, based on this definition from Ross then takes it as a theorem that this definition is equivalent to the quote-unquote typical definition of delta epsilon. So as a theorem, then it has a proof. And Ross proves this statement that that Taalman took as a definition. Let f be a real-valued function whose domain is a subset of the real numbers. Then f is continuous at a point in its domain if and only if, for each epsilon greater than 0, there exists a delta greater than 0, such that if x is in the domain of f and the distance between x and x naught is less than delta, that implies that the distance of the values of the function values is less than epsilon. Remember that this notation, bar a minus b, this is called the absolute value function, and it is a minus b. If a is bigger, then it's a minus b. Otherwise, it's b minus a if b is greater than a. So that will give you the distance between two real numbers. So this is the difference of the distance, the difference between the y values is close to epsilon. And here is the anytime that you have two x values within the neighborhood, that the y values are within the desired voting result. Ben, if you're still there, I came up yesterday with the idea of trying to define epsilon-delta and the game of picking a delta based on epsilon. It's kind of like gerrymandering, right? Like redrawing political maps if you want like a given political result on a vote, where delta, like we're going to redraw the neighborhoods such that all the neighbors within that neighborhood enough of them vote close to L, to the voting result that, not all of them need to vote on L, but enough of them do that the voting result will be the political result that you want. I feel like there's something there. Like, you can kind of call this gerrymandering. Like, let's redraw the political map so that we get the voting result is going to be close enough to L, like within epsilon, like within our, I don't know, what would epsilon be? Like, probability of getting sued? Probability of getting caught or sued for cheating election results? That's a nice analogy. You could do it with balls in R2 as well to make it an even closer analogy. Why would balls in R2 make it even closer? I mean, I agree with you that is the next step of abstraction, and we're going to get there in a moment. But yeah, like, within a certain distance, like, drawing neighborhoods so that that all of the neighbors within that region vote the same way. Okay. Or enough neighbors within that region vote the same way. Yeah. All right. So now we're going to go from yellow to red. So math up. How's it going, Ace Piggy? How are you? So we're still in... I don't even have my copy of Ross anymore, unfortunately. I sold it or lost it or something. But now we're going to get to these books, and hence the thumbnail. We're going to get scarier. We're going to get scary as hell. We're going to see a few more definitions of the limit of a function, according to these horrible people. So I call this one Tiny Spivak. Spivak also wrote a beautiful calculus book that's large, and it is meant for a first course in calculus, but it is still an analysis book. It is still Epsilon-delta. It is still fairly pure math, but Tiny Spivak is... Whew. All right, so I've been writing down page numbers. Ross defines delta epsilon on page 124. From now on, we're going to be much more just reading. I'm going to be reading you a scary bedtime story. Definition, Tiny Spivak, page 11. A function, and now one thing is, as the books get scarier and tinier, he does not put this in a box. It's just a paragraph. Like, you just read this and it's just paragraphs, and it's just a story that he's telling. He does box the theorems, but Spivak does not box the definitions. So this is just part of a paragraph. A function from Rn to Rm. So Spivak is right out the gate. We're talking about multiple dimensions. Any number of dimensions. Not just not just the xy plane, but from n-dimensional to m-dimensional functions. A function from n dimensions to m real dimensions is a rule which associates blah, blah, blah. So a couple lectures ago or videos ago, I talked about how, it's kind of hard to define a function. You have to just call it a rule, I think. And so these people do the same thing. The notation limit x tends to a, f of x equals b means, as in the one variable case, that we can get f of x as close to b as desired. So we're going back to metaphorical language again. We can get f of x as close to b as desired by choosing x sufficiently close to, but not equal to, a. In mathematical terms, this means that for every number epsilon greater than 0, there's a number delta greater than 0, such that that the y values, the function value of x is close to b. It's within epsilon approximation of b for all x in the domain of f, which satisfy 0 less than x minus a less than delta. For every number in the domain that is close to delta. So again, this is just like how in Taalman she writes for all x in c minus delta. C minus delta to c union c to c plus delta. Like the fact that this is 0 strictly less than that distance is the same as omitting the point C. So anyways, a function f from A to Rm is called continuous at a point A in A if limit f of x equals f of A. So it's called continuous at a point if the limit equals the value. So I don't think we did this on the other books or something, but I haven't shown this before, but in this case, the limit as x goes to 0 of f of x is 0, but maybe we define the function differently so that there's like a jump, and in this case, the limit doesn't equal the value at the point 0. So this function is not continuous at 0. So that's the same idea there. And f is simply called continuous if it is continuous at each point in its domain. One of the pleasant surprises, ... and then we get into some scary territory. Hey, Math Spellbook. Yeah, hope you're doing well too. Good to see you. All right, so we're getting through some calculus and really analysis. Okay, so that is tiny Spivak. And notice, I just want to draw attention to the fact that this is page 11, whereas all these other ones were page 124, on and on. Now, Rosenlicht, I'd say, is just as hard or just as scary, one might say, but we're going to get into weirder territory now with Rosenlicht. So I looked in the index and I found limit, and again, Rosenlicht defined limit in terms of sequences first. And I was like, okay, cool, that's just like Ross. And then it says, let P1, P2, P3, ... be a sequence of points. Okay, that's familiar. In the metric space. Wait, what the hell is a metric space? So, whoops. Failed take. We got to figure out what a metric space is. Let's jump back from page 45 to page 34, what the hell is a metric space? A metric space is a set E together with a rule which associates with each pair P, Q in E, a real number, D, P, Q, such that D, P, Q is greater than or equal to 0 for all P, Q in E. Distance, so I'm going to start saying distance because that's why we use the word D here. And a metric is a distance function. So a metric space is any space where you can talk about how far away 2 points are. It's not always going to be the regular notion of distance that we're used to. We can define other types of distance. Very briefly, there's the saying, quote unquote, the distance from Tokyo to New York or something, like as the crow flies, or from my house to the airport, is a straight line as the crow flies. Like if a crow flies from my house to the airport, that is a straight line, but if I'm driving my car, I can't drive the same straight line to the airport. You could talk about like a highway distance or like the distance based on roads, or even further, there's something called the taxicab metric. And here, as the crow flies between 2 points is the straight line between them, but the taxicab metric is going to be first you travel y points down and then x points. So it's like straight lines only. That's called a taxicab metric, as opposed to the traditional Euclidean distance. Euclidean distance is like the Pythagorean theorem, whereas if you're driving a taxi cab, you can't take a straight line. You're going to run into a lot of people and buildings if you do that. So you need to take the roads if you're a taxi cab. Otherwise, you're not going to get any tips. All right, metric space is this. So we have some concept. We have a function that will tell you how far apart two numbers are. So as long as the distance is always non-negative for any 2 points, like that's a weird concept. What would it mean to have negative distance between 2 points? Okay. The only points where the distance is 0 is if the points are equal. Every separate point has a distance between it. That's important. Okay, and then driving from point A to point B is the same as driving from point B to point A. Like, the distance from here to there equals the distance from there to here. And then finally, we have this idea of a triangle inequality. So if you take a pit stop driving to some location, then that's going to be longer than if you went straight to that other location. Like, taking a pit stop somewhere else will always make your trip longer. Like, your distance is going to be longer if you take a pit stop between points. I'm going to use ABC because I'm a simpleton. Going from A to B and then to C has to be longer than the straight line from A to C. Anytime you draw this, you create a triangle, so that's why we call it the triangle inequality. Okay, so that's a lot of familiar concepts from the real numbers, but then it turns out that, for example, this taxicab metric, you can see that the taxicab metric does satisfy all of those requirements. So it creates a different metric space than the standard Euclidean distance. And so, what the hell are we doing again? We're defining metric spaces, and we are defining a limit of a sequence. So Rosenlicht defines limits of sequences in an arbitrary metric space, anywhere where you have the idea of distance. That's cool, but that's getting weird as hell. Okay. Then here I wrote this, take 2, we're going to try this again, limit of a sequence. Let this sequence be a sequence of points in the metric space E. A point P in E is called a limit of the sequence, P1 ... if given any real number, there's a good old trusty epsilon greater than 0, there is a positive integer n such that the distance between the limit and your partial point Pn is less than epsilon whenever n is greater than capital N. So that's stating the same definition that we saw before, but now we have, instead of absolute value P minus Pn, now we have distance between P and Pn. So here we're abstracting the concept of the difference, the Euclidean distance, to an abstract distance. If the sequence P1 ... has a limit, we call the sequence convergent. And if P is a limit of the sequence, we say that the sequence converges to the point. So that's kind of similar to some of the other definitions we saw. Leo lectures. Negative distance sometimes comes up in computer science, but you usually have to be careful with it. That sounds really interesting. I don't know anything about that. I would love to know that. I know, that you have something called like the Hamming distance between two numbers, and I think that creates a metric space, the Hamming something or other, but I don't remember. I'm pretty interested in what that means, what you're referring to. All right, so now, page 45, we've got the limit of a sequence again, but now it's in a more abstract metric space. And now, page 72, now we have limit of a function. Great. All right, so now E and E prime are two different metric spaces, and P naught is a cluster point of E. What the fuck is a cluster point? And let F be from squiggly C of P naught into E prime be a function. What the hell is squiggly C? A point Q in E prime is called a limit of F at P naught if the function from E into E prime, which is the same as F on cursive C P naught, and which takes on the value Q at P naught, is continuous at P naught. This is the point where my brain is shutting off and I'm like, I used to be smart, I used to understand this stuff. I am no longer smart. I do not understand this anymore, and that's okay. I will get there. We're going to practice and we're going to get back to this, maybe not. So cluster point, don't really remember that exactly, but and then fancy C of P naught, I think that is like the set of compact spaces around P naught or something. I know that compactness is another important idea here, and all this stuff is getting very complex and hurting my brain. I believe cluster point has something to do with compactness as well. I don't remember it at all. I'm very confused. I wanted to say this is all thanks to this guy, Fréchet, in 1906. He came up with the idea of metric spaces. So now we're starting to get into really new territory. Like 1906, that is not that long ago. So we're abstracting, we keep getting more and more abstract. Page 73, how is this different? Let E prime be metric spaces. P naught is a cluster point of E. From compact spaces around P naught or something like that. Be a function. Point Q is called a limit of F. Limit of F at P naught. If any epsilon greater than 0, there exists a delta greater than 0, such that if P is in E, the point P is not P naught, and the distance is less than delta, then the y value distance between FP and Q is less than epsilon. So the shape of this looks familiar. This is really similar and feels familiar to the prior ones, but now we have some much more abstract general metric space idea. So anywhere where you can define a distance between 2 points, we still have the idea of a limit of a function at a point, which is cool. All right, so I'm gonna catch up with chat in a moment here, but I want to keep going. All right, we're gonna keep getting fucking weirder and weirder though. Gamelin and Greene. In a sense, this is a reaction channel. I have not opened this book until today. I just got it. It's like $15 or something from Dover. Beautiful book, from what I can tell. I know from my classes that topology is a more abstract concept. And we briefly got a hint of this back from Spivak, where he says he has this scary note. One of the pleasant surprises, ... and I left that for now. One of those pleasant surprises is that you don't need to even have distance in order to define continuity. You don't even need distance at all. A topological space is a space where two objects are the same even without considering distance. There's a very tired joke that a mathematician can't tell the difference between a coffee mug and a donut. A topologist can't tell the difference because even though the points of a coffee mug are totally different and the shape is really different in Euclidean space, like if it were Play-Doh and you could squish and smash it and rearrange it, you would get a donut. You would get a cylinder with one hole in the middle of it. If you stretch and mash together this coffee mug. So now we're getting into a new concept of continuity and defining topological spaces where we don't even care how far apart those points are. The distance, we don't need the distance thing. Let XD and... Oh, but first I will say that Gamelin and Greene, they also spend a chapter on metric spaces first. And so here we're just repeating the same metric space definition. I think it's a little cleaner, but XD and YP are metric spaces. I think that this is X and Y row, which is just a little rounder. A function f x to y is continuous at x if whenever this is a sequence in x, such that the sequence converges to a point, then the values converge to a point. The function f is continuous if it is continuous at each point. So that is a metric space definition, and it is so much less scary to me. It's like less formal than this one talking about a cluster point, and apparently we are still talking about sequences of points. So this is a little bit more straightforward and easier to see without the whatever the hell a cluster point is. Now, that's a definition, and then here we have a theorem. So this is something that you can prove from a definition. The function is continuous at the point x if and only if, for every epsilon greater than 0, here's our good old classic, lovely Epsilon-delta definition. So again, we're not taking it as a definition. It's actually a theorem. It's a result from something simpler. But it takes a lot of work to get there. So again, Taalman calls this a definition, but if you keep studying mathematics and keep understanding all the assumptions, you can find that this definition is actually a result of something more abstract or more simple. So yeah, we've got continuity at a point, and the distance, if the neighbors are close, live close enough to each other, then they vote the same. They usually vote the same. That's going to be my gerrymandering analogy to epsilon-delta proofs. Now, Gamelin has this. The following are equivalent. 6.1 and 6.2. We've already showed that because 6.2, the epsilon-delta, this is the theorem 6.1. And then this last one, this one is new. F inverse V is an open subset of X for every open subset V of Y. What the hell does that mean? This here is what Spivak said was a delightful surprise. He also proves the same thing, that the definition is consistent with this other idea that whatever an open subset means, there's something else that doesn't require the concept of distance. So, what is an open subset? Now we're going to get to coffee mug versus donut territory. We've got this guy to blame for that. Hausdorff, 1914. He's the person who, throughout his life, was always struggling to tell the difference between his coffee mug and his donut. And then he created a lot of math to try to understand the weird ways that his brain worked. Topological spaces. Let X be a set. A family cursive T or cursive J. I couldn't tell which it is. I'm going to guess cursive T, like fancy T, of subsets of X is a topology for X if fancy T has the following three properties. Both X and the empty set belong to T, script T. Any union of sets in script T belongs to script T, and any finite intersection of sets in script T belongs to script T. So now everything is being defined in sets. We're talking about an empty set, we're talking about unions, and we're talking about intersections. And I suppose we're also talking about finite as opposed to infinite. So now we're talking about something more abstract. We're talking about sets. And we're back to like this thing that's hard to define. A topological space is a pair x and script t, where x is a set and script t is a topology for x. Remember that we just defined what a topology for a set x is. The sets in fancy T are called open sets. So now we've got the definition of what an open set is. An open set is a set in a topology. Okay. Now, on page 62, a sequence of points in a topological, so again we've got sequences, in a topological space X converges if for every open neighborhood U of X there is an integer n such that xi is in U for all I greater than n. Do we have an open neighborhood? I think I would need to define what an open neighborhood is, but what the heck is an open neighborhood? Anyways, at this point, I don't understand anything anymore, and my brain is hurting, and I just want to start calculating how far I can throw a baseball. And I've got a differential equations book around here somewhere. We're gonna get back to some concrete math in a little bit, but I just wanted to show everybody that this idea that Taalman has in her book, that's like the intuitive description for a limit, as opposed to the formal definition of a limit. If you chase that rabbit hole, it goes really, really far. Like, you can just keep pulling that thread and keep finding more and more abstractions and more interesting things. Like, what if we remove the idea of distance? Or what if the distance was different than what we're used to? Do we even need distance at all? Can we create something like calculus on Plato instead of our normal world that we live in? Like, we started defining things farther and farther away from the real numbers. Spivak is scary as hell. I wrote it in red, but he still assumed that we're talking about real numbers that we are used to. He still assumes just real valued functions. Rosenlicht says, okay, doesn't have to be real valued functions, we just need a metric space. And then topology, we start defining a limit without even needing the real numbers at all. We are talking about a more abstract world of sets. So topology starts defining things on this idea of set theory, of just like a collection of points, and something called a neighborhood. Like whatever neighborhood is. Okay, it sounds like we need to understand this, but is there something more abstract than a set? Is there something even more abstract than this? This idea feels very abstract. Well, guess what? That rabbit hole just keeps going farther and farther. You can define things like categories, which kind of are like a more abstract version of a set. And that's about where my brain is turning off and I'm ready to go. So thank you all for listening to this rant about how scary mathematics can get. And if you are watching this still, like and subscribe first. But then secondly, if you are struggling with mathematics, I hope that there's somebody out there who's enjoying this and just learning calculus for the first time, that would make my day. Please comment in the comment section if you are in Calculus 1 and you found this video interesting and you learned a little bit about how weird calculus can get. Yeah, that would just make my day if you enjoyed this. And if you are in high school or Calc 1 or any level of math and you're struggling with it, just know that that's normal, because math just keeps getting weirder and weirder and harder. It is, in a sense, infinite. It is infinitely difficult, and people just keep coming up with weirder and weirder ideas, and it's just such a deep question. Are we I feel like we are definitely discovering math. We are discovering some true statements of the universe at some point. Some of this math that we're talking about is a true scientific observation about the universe. But then, at what point are we inventing math? At what point here are we just playing an abstract game where we're inventing ideas that don't exist in the real world at all? Where is that line? Where is that line? Are we discovering scientific observations of the universe at this point? I would say yes. I would still say that yes, we are still discovering mathematics, but then at the same time we are creating and inventing mathematics. And to me, that is what's beautiful about math. It is useful, but it's also an art form. We are discovering math and we're able to use it. Even this stuff, topological space, you will see books that are talking about topology applied to machine learning or whatever. Especially in computer science, some of these super abstract ideas are being found to be useful. If you analyze the graph of a network of some kind, a data, topological data sets or something. So I just think it's so dang cool. It's an art form that's also very useful sometimes. And yeah, I don't know, no matter what, it stretches your brain and you get really good at problem solving if you just study math. Yeah. Even if it's never useful, I've never in my life, ever since graduating, I have never needed to calculate a topology on a set. I have never needed to recall or write down a single Epsilon-delta proof or, no way. Never needed that in the real world, but I think that studying this stuff has given me some superpowers in problem solving, because when I come across a problem at work about learning how to use a new framework that Apple released for iOS apps, and it's confusing and it's hard, I can go back and think, it's nowhere near as hard as some of this stuff. Refactoring legacy code and making sure that you don't break something as important as payments for some system, that's nowhere near as difficult and hard as some of the harder problems that I've done in the past. So I have a level of confidence, I think, in my problem-solving skills, because I can come back and think, you know what, this is not as hard as metric spaces or topology, or working through Spivak. And that's useful. And I think that finding that love for problem solving at any level of mathematics is going to stick with you throughout life, because you will be able to solve hard problems, and you'll be able to think back to when you were stuck and couldn't understand something like this, but then you did, and you had a light bulb moment, and it was wonderful. All right, this was fun. This was super fun, y'all. I'm going to take a short break. Speaking of coffee and donuts. I'm going to take a very short break. I'll be right back. I'm going to refill this coffee mug. I'm going to come back and I'm going to answer some chat and questions and hang out with y'all. I see, yeah, we've gotten a good amount of chat today. I see Leo Lectures, Math Spellbook, Ben H, Sam. Cheers to you all. Thank you for joining this. I hope you enjoyed it. I think it was really fun for me. Okay, be right back. I'm going to get some coffee. Tomorrow we're going to get back to easy calculus. If any of y'all want to buy me a coffee, you can go to thanks.themathhobbyist.com. But absolutely no pressure. This is all given freely with no expectation in return. But I do drink a lot of coffee, and if I get more coffee, I will turn it into more proofs and more weird lectures like this. All right, be right back. All right, y'all, what's going on? So, you're back. I'm so excited to read this because we have actual mathematicians in the chat, people who actually understand this stuff infinitely more than I do. So I'm very excited to catch up. All right. Yeah, I didn't want to take too much of a break in the middle of the presentation because I hope that this video can stand alone on its own as a YouTube video. And anytime that you like really take big breaks, you know, to respond to chat, it kind of breaks the flow of a regular quote unquote YouTube video. So let me see if I can put chat up on screen. Thanks for the likes. I see we have 2 likes. I appreciate it very much. Thanks, y'all. If anybody else out there likes this, hit the like button. Here's a good little reminder and opportunity. Hey, thanks, man. I appreciate it. All right, let's get chat up on screen. Okay, I guess I can't really scroll in that chat window, so too bad. Oh well. What can I do? I can at least get some more of this on screen if I do this. And then if I increase this height a lot. See, like, this sort of stuff always breaks the flow of a video, unfortunately. As much as I would have loved to chat on screen more. Let's do, what is it, 1440? Nope, that's too much. I'm a dummy. What's the resolution on this thing? 1080? Whatever, that is close enough for me. Okay, so we're still not going to get everything in this little chat window that I'm pulling up, but I'm going to read, and at some point we'll catch up. So, negative distance, Leo lectures, negative distance, it comes up in arbitrage algorithms. Essentially, you have to avoid any negative distance cycles. Otherwise, you get negative infinity distance between two different points. That's interesting. That's super interesting. That sounds kind of like that, like error correction codes. Does that have anything to do with error correction codes? And like, I think that that's what Hamming distance has to do. Arbitrage or something, like if like, I don't know, some cosmic ray hits a bit and like flips bits or something. I don't know. Oh, Ben H, I think drawing on an actual map could be interesting, hence using R2, if you see what I mean. Absolutely. So I think you're absolutely right. I just realized that you were saying R2, not R3. I thought you were saying three-dimensional balls, and I was like, that would be hard to draw. But yes, drawing on R2, like an actual map, and drawing like gerrymandering distances or neighborhoods and stuff, I think that would be so cool as a metaphorical explanation to Epsilon-delta proofs. I'm not prepared to try to do that on the fly today, but maybe in the future. I think that that would be such a cool video. And just introducing the idea of gerrymandering. I've seen a really awesome set of math that tries to solve the gerrymandering problem by treating them as like, by using compactness and like the topological concept of compactness. I don't know. I've seen some topological treatment of the gerrymandering problem that looks really awesome, and I don't understand anymore at all. Wonder what flight the crow is trying to catch. Yeah, where's that crow going? That crow wants to go to Tokyo or something and needs to get on a plane. Negative distance, says Leo lectures, and some other stuff. Let's see. So I'm like really catching up. It's fine if these are unintuitive. Issues with dealing with limits of functions lead to the crisis in foundations of math. Yeah. Okay, so that's the crisis in foundations. I alluded to that there was a crisis in the 1800s and mathematicians got really upset. And it's because we tried to put math on formal ground. We kept hitting these errors. We started getting to these weird ideas of like Cantor sets and like, wait a minute, what do you mean you can have multiple infinities? That is a disease that mathematics will someday recover from. Like that's cool. I didn't know that limits of functions led to the crisis in foundations of math. It is, right? Or yeah, I think I was saying that. That's why we put epsilon-delta proofs, like got the rigorous epsilon-delta definition, and there was a crisis in mathematics that required it. It's subtle stuff. Ben H says, I love this, aha, that's great. We did a lot of this stuff, the modules before Hilbert spaces and functional analysis. Whew, I wish I knew what you mean. I've always heard of that. It always felt really nicely put together. Like a lot of this stuff being like contrasting definitions, like from different books. Is that what you meant by that? A lot of this stuff on the modules before Hilbert spaces and functional analysis. I think it's always great to directly compare and contrast two different textbooks on the same idea. And if I could talk to former me, I don't know, like a college class, you don't have the time to do it. But if I didn't have a social life, or if I didn't get drunk all the time, I would say, instead of getting drunk all the time, get another math textbook for every course that you're taking and compare the two. Like, try working through an equal difficulty textbook at the same time, work more problems. You're going to be proud of that way more than socializing all the time. Just everything in moderation, you know? So, instructions unclear. Ate my coffee mug. Exactly. I thought it was a donut. Damn it. I have to create mathematics to understand why. Let's see. LMAO. I don't know what you're laughing at, but I'll find out later maybe. Are you a student? Leo, sort of. Currently on leave. Might go back to study soon. Cool. Leo, so what do you study? Are you studying math? Yeah, math students. You can go to limits of general sets, objects, etc. if you go into category theory. Hell yeah. Yeah. I should have thought of that. I should have remembered that. Yeah, you can define the limit of sets and like limits even more abstractly, like from this book. That's cool. It's just awesome to watch you going through the pureness of the subject. Hell yeah. It's just fun, I think. Like, I just find it gorgeous. Math Spellbook also has a stream like this on Twitch. And a little bit easier math, I think that's fair to say, right? Like, more Calc 1, Calc 2 physics. But, like, the same level of awe that you have about mathematics. It's like, I open this and I feel like I'm reading a spell book in the, like, fabric of the universe. Like, I absolutely get the same thing. Like, no matter what, I think, if you just read super abstract math and try to understand 1% of it, you feel like you're gazing into the deep fabrics of the universe in like a really beautiful way. Absolutely. As I've learned math, I've come more to math-invented perspective. Me too, honestly. I think it's both, but I think that there's a lot of math that we invent, like just straight up invent. And it may or may not ever be useful, or 99 point whatever percent is never going to be useful. But we invented it, and I don't know, it's nice. It's just nice. And it was there. It was ready to be invented someday. Like, if you just follow logic, it's been sitting there, ready to be invented, ready to be discovered. So, I don't know. Like, it's just both. Invented and discovered, I think. Yeah, it's like math is being discovered from another realm that is part of our reality, or some blueprint of our reality. Yeah, it's like in number theory, how we didn't use it until computers became more mainstream. Yeah, exactly. Like, I mean, yeah, Hardy, if we go back to... This was so cool to me. I did not know that... Oh, you can barely see it. Hardy is the person who created the notation that we know and love, even in Calc 1. He wrote down limit with the arrow below it. And that's new. That's really cool. But yeah, like, he said that number theory was the queen of mathematics and that it's the most beautiful mathematics, and he can die without feeling any guilt because number theory will never lead to a nuclear bomb. Studying prime numbers is harmless, and like, maybe it's useless, but at least it's not harmful, was what he was saying. And then we invented Bitcoin. So, like, oh no, I'm sorry, Hardy, you invented something as bad as the nuclear bomb. Arguably. All right. You know, just in the last few years, essentially a new definition... Ooh, I don't know anything about this. A new definition of topological spaces was invented, I would say, because of problems with topological spaces. That's cool. I don't know anything about that. That sounds really cool. Awesome. Leo lectures, student or someone doing math as a hobby, sometimes student, sometimes researcher, might try making math videos. Hell yeah. Let's create like a cool little group, like a little like community of math hobbyists, students, former mathematicians, people making hardcore educational content for fun, right? Like, I think that's awesome. I'm gonna make sure that I follow you. I hope that you start uploading some videos at some point. Okay, so I guess I can read here. I thought you were presenting great. Thank you. Thanks. I'm glad that you enjoyed it. You enjoyed it. You enjoyed the presentation. It means a lot. While you were reading all the definitions, I felt so lost, and I'm just doing trig substitution problems, lol. Well, yeah, if you're doing trig substitution and you're trying to understand this really complex stuff that's completely out of context, and no reasonable course in their right mind, no lecturer would ever present all this stuff in one lecture. Like, it's stupid. There's a reason nobody does it this way. Like, you're not going to understand it. But I just want to impart a little bit of flavor. Like, I just want you to get 1% of this idea that, like, there's this definition, but there's all these other, for what's a definition for one person, it's a theorem for another person. And, you know, one person is going to define it in terms of simpler things, and then you can just pull that thread and go all the way down, turtles all the way down, as far as you want in mathematics, and keep, like, building more and more abstract spaces that are more and more beautiful or useless and ugly, depending on your perspective. I'm thinking of making a video on multiple types of infinities. Yeah, I'm thinking of that too. Like, that's one of my favorite party trick facts that I would tell people at a party. It's like, did you know that there are multiple kinds of infinity? There are different types of infinity in a very real way. And then, yeah, that's a really good one. We should both do our videos. Like, there is enough space in the world for an infinite number of multiple infinity videos. We will definitely get there. I think comparing the evolution of the definitions is nice, especially continuity and limits. Yeah, I thought that was cool. And writing down and researching, like, the historical years and historical idea, or like just writing down who came up with this idea was like a very last minute thought right before I hit go live. I was like, I wonder if I can write down some years, like, when was all this, like, invented, and who do we have to blame for each of these things. Also, in my opinion, you should not try to make sure you understand everything during a math class. Good idea. Get problems done and get exposed to a lot. You'll understand later. That's perfect. That's something I wanted to do in this video. It's like, I don't understand what I'm writing down. Like, right now, my brain hurts. I am going through caffeine withdrawal. My brain hurts, but I can at least just write down this thing. And I can get some muscle memory just writing down this thing about a cluster point. And you know what? I don't have time to figure out what a cluster point is right now, but I know that Rosenlicht defines limits in terms of cluster points in a metric space and something called fancy C. Like, I can learn a little bit there, and then I'll come back to it. I'll do that repetition. I'll come back again and again when I'm doing the problems, and over time, just rote memorization, just rote muscle memory of writing down the thing. Over time, I'm going to understand that better and better. Yeah. Thanks for the shout out. Yeah, of course. No worries. Math, computer science, student, and researcher. Hell yeah. What I'm better at is algebraic/topology stuff on math side, cryptography, complexity stuff on the CS side. Dude, we're gonna be friends. I want you to keep showing up to these, because I really want to learn cryptography, and someday complexity theory as well. I really love number theory, and I love algebra. So I've never really dove into cryptography other than like a little module on cryptography in my intro to number theory course. So I know like a little bit about what cryptography is, and you multiply two humongous primes, and then it's hard to figure out what those primes were, and therefore you can send secret messages to your friends. Yeah, and I love algebra, but I've never applied algebra anywhere. Like, I've taken abstract algebra courses several times, and I always love algebra in and of itself, but I've never taken a class or worked through a book applying algebra to something like algebraic geometry or algebraic topology or even algebraic number theory. Like, you see a little bit of that in those courses, but the courses of algebra that I took were pretty straightforward on algebra in and of itself, which is beautiful. I did take one course that was on groups and representations, and it was an undergrad representation theory course, and it was really nice. And so that's like groups and abstract algebra applied to symmetries and understanding the symmetry of an object. Yeah, and that's kind of the beginning point of it. I actually think more of it is useful than people realize. Cool. Like, I was using ring theory stuff and concepts from complex analysis in a paper I did in computer science. Hell yeah. Yeah, no, I've definitely thought of rings. I'm blanking on a concept. There's something where I have like kind of like a theory around like software architecture. I'm going to come back to this in the future, but I've definitely thought of rings and categories and applying both of those abstract ideas to like a theory of software architectures. Like, yeah, I'll talk about that in the future. But oh, Math Spellbook, I missed you, but thanks for stopping by. Yeah. Hell yeah. Positive vibes, lights, energies, wishes, and unexpected wonders to all you guys. Take care. Yeah, man. Good to see you. Thanks for swinging by. Elliptic curve cryptography has a ton of algebra. Oh, absolutely. Yeah, that is what I would love to understand. I want to understand the theory of elliptic curves and Fermat's last theorem. Like, I know it's such a common thing that people love Fermat's last theorem. I want to understand the proof. I want to understand Wiles's proof of Fermat's last theorem as a hobby for fun, Pretty hardcore stuff. Yeah, representation theory is stuff I definitely want to learn more. Me too. I really want, because it was fairly accessible. Like, the teacher I took it from, the professor, was like, she did a great job at presenting it like to an undergrad level. Like, you didn't need to be a PhD in math to take this one. Like, so there's a way to study representation theory in like an informal elementary level. I mean, with the language of groups and abstract algebra, but you basically need groups in abstract algebra and linear algebra in order, and then you can start studying symmetries of objects and representations of those symmetries, which is really cool. All right, y'all. Well, so I caught up on chat. Thank you for hanging out, and yeah, for your company. I hope you enjoyed this. If anybody makes it to the end of this video, let me know. Drop a comment in the comment section. I hope you enjoyed this. My name is The Math Hobbyist, and yeah, if you enjoyed it, hit the like and subscribe, and join the Discord. You can go to discord.themathhobbyist.com. All right. Representation theory to me is basically the generalization of diagonalizing a matrix. Yes, that is my super rough understanding as well. All right. Thanks, everybody, for watching. Have a wonderful, beautiful day. Go do some math or go do something